I welcome all of you to the video lecture series on fluid dynamics. This lecture is on boundary layer theory. In this lecture, I'll start with an introduction to boundary layer, and then I'll move on to scaling analysis, where I will show you the derivation of the Prandtl's boundary layer equation. Thereafter, I'll discuss the three types of boundary layer thicknesses and present the non-dimensional expression for various boundary layer thicknesses and wall shear stress. Finally, I'll present an important fluid dynamic phenomena that is called as flow separation for a boundary layer. So let us, in this slide, I'll try to answer the two important questions that comes to our mind in this topic is what is boundary layer and why do we study it? So it is a very commonly encountered situation that whenever flow takes place over a solid surface, which could be either stationary or it could be moving at certain velocity. So let us consider a solid surface, which is like a horizontal plate over which there is a fluid flow which is occurring. So let us suppose this is the horizontal flow which is occurring over a horizontal flat plate. So when the flow occurs, this plate is stationary. So there is a boundary condition which is called as no slip boundary condition at the wall, due to which the velocity of the fluid at the wall is zero. But gradually what you observe is there is an increase in the velocity, and the velocity increases up to a certain maximum value corresponding to the uniform velocity at the inlet. So at an actual location x1, you can see that when the fluid passes through this at an actual location x1, there is a gradual increase and the gradient is within a certain height of the layer. So this is denoted as delta x1. And another downstream location x2, the height of the fluid layer in which you have a velocity gradient is delta x2, and further downstream it is delta x3. So what you observe is as you move downstream over the surface of the plate, the thickness of the fluid layer across which you have a velocity gradient del u by del, if vertical direction is y, the height of the fluid layer on which del u by del y is non-zero is presented by this height, which is gradually increasing. And if you draw the locus of the point of the height at which the velocity is almost equal to u infinity, which is the inlet velocity, then you end up with a line which is called as boundary layer. So this is the layer below which you observe. So this is called as this is the boundary layer is the layer or the locus of the point up to which you see the velocity, the non-zero velocity gradient, and below this boundary layer you have a boundary layer region. So in this boundary layer region, you observe you have a non-zero velocity gradient, and outside the boundary layer you have a del u by del y almost equal to zero. So note that in any fluid mechanics problem, the action in a fluid mechanics problem start when you have a solid surface. Such as in this case, this surface can be like a top surface of the car, which is horizontal, and there is a free stream flow. The fluid is moving over the, let us say, top surface of the car by a uniform velocity, and so in that case you observe this type of velocity gradient above the surface of the car. So if this solid surface, if you don't have the solid surface, the fluid which is moving with a uniform velocity keeps moving with a uniform velocity. The action, when I say the velocity, I mean the velocity gradient, the onset of velocity gradients appear only when you have a solid surface on the path of the flow. So in this case, when you have a flat plate on the path of the flow, you end up with a velocity gradient within a narrow region which is called as boundary layer. This thin region in which you have a velocity gradient plays a very important role because it gives us certain engineering information. Like for this problem, when the fluid passes over this flat plate, it tries to drag this horizontal plate along its flow direction. So there is a force which acts, which tries to move this flat plate along the horizontal direction. So why we study the boundary layer? Because for flow over a flat plate, such as in this case, we need to determine the net force acting on the plate when the fluid passes over the surface of the plate, and this is obtained because the force which acts on the surface of the plate is basically a shear force. So when you take a surface integral, if W is the width of the plate perpendicular to the plane on which it is shown, and you take an elemental length delta x, so this is the surface area on which you have a local shear stress tau W. And now this hydrodynamic shear stress is given by mu del u by del y. That is the normal gradient of tangential velocity. On this horizontal surface, the tangential velocity is u. So to calculate the shear stress, wall shear stress locally at different axial location, you have to calculate del u by del y, which is, this is the velocity profile. So at this axial location x1, if you calculate the slope at wall del u by del y at y is equals to 0, this is important. So at this location you can see that the slope is more. As you move downstream, the slope is reducing. So the wall shear, local wall shear stress reduces along the as you move downstream on the plate. And this, so to calculate the wall shear stress, you need to calculate the velocity gradient at wall, so which is inside the boundary layer. So, so you need to study the boundary layer, because from the boundary layer theory you can obtain this velocity gradient. And once you know the velocity gradient, you can calculate the local wall shear stress, and you can calculate the total shear force acting on the surface of the plate. So this most of the engineering information, or most of the velocity gradients, uh, the velocity gradient inside the boundary layer is extremely important for us, because it gives us certain engineering information. So that is so this is the reason we are studying the boundary layer theory. This is the velocity profile which I had shown you earlier for a laminar flow. If you consider a turbulent flow, then what you observe is a much steeper velocity gradient near to the wall. And this is because along with the streamwise velocity, in a turbulent flow, you have a velocity fluctuation. So the fluid particle which is moving on a horizontal layer, it has a transverse velocity, v velocity, and which is varying in time. So when a fluid particle is moving in a laminar flow, the fluid particle on a horizontal layer keeps moving on that same layer. Whereas in a turbulent flow, a fluid particle along with the u velocity, it also has certain small v velocity, which is periodic in nature, which has certain amplitude which changes from positive to negative. So the fluid particle moves upward and downward with respect to time, and it is chaotic motion, which leads to a better momentum transport, uh, which leads to the mixing of the momentum transport and leads to a much larger velocity gradient near to the wall. So this velocity profile corresponds to the turbulent boundary layer, and this blue color velocity profile corresponds to the boundary layer for a laminar flow. So in a turbulent flow, you can see that the velocity gradient near to the wall are much larger, and you have a much larger wall shear stress and shear force for a turbulent flow. As I mentioned in the previous lecture on the derivation of Navier-Stokes equation, and when I had presented the analytical solution, that exact analytical solution for the Navier-Stokes equation is possible for some very simplified situation. For most of the problem in fluid dynamics, we do not have an exact solutions. So uh, if you look into the analytical or semi-analytical methods for solution of Navier-Stokes equations, we can obtain the exact solutions for some very simple situations. However, with certain simplifications, we can obtain some approximate solutions. So we can simplify the Navier-Stokes equation for certain regions in the flow, for which we have some mathematical techniques, uh, through which we can obtain the approximate solutions, such as for in some fluid region, if the flow is stationary, then for fluid statics, we can obtain the analytical solution. If you consider certain flow region where the flow velocities are extremely small, which is called as creeping flow, for those situations, those flow regions, we have mathematical techniques to obtain the analytical approximate solutions. There is a separate subject within fluid mechanics, which is called as inviscid flow theory, which I'll discuss in the next slides. So for considering the fluid as almost fluid of very small viscosity and incompressible flow, for this class of flow regions, there are certain regions in the flow where the the effect of viscosity is negligible. For those flow region, there is a theory on inviscid flow theory through which we can obtain the analytical solution. And corresponding to this topic on boundary layer flow, I will show you a little later that we can simplify the Navier-Stokes equation, which changes the nature of the Navier-Stokes equation and make it simpler, which is amenable for analytical solutions. So these are some of the situations for which we can obtain approximate solutions using either analytical or along with analytical. In some cases, we also need some numerical methods, and that is called as semi-analytical methods for solution of Navier-Stokes equation. In the early days of fluid mechanics, this is the theory which was very popular, which is called as inviscid fluid flow theory, and this was called as a subject called as hydrodynamics. So in this subject of hydrodynamics, the fluid was considered as an ideal fluid, and when the ideal fluid corresponds to a fluid which is incompressible and which has a negligible small coefficient of viscosity. So in these cases, the viscous forces are considered negligible, and there is a balance between the inertia and the pressure forces. However, this inviscid fluid flow theory, in the early days of fluid mechanics, there are a lot of mathematicians who considered the fluid as ideal, where they consider incompressible and negligibly small coefficient of viscosity, because then it becomes, with this conditions, it becomes amenable for analytical solutions. So using this inviscid fluid flow theory, they have presented the results, but those results had serious limitations when you compare with the experimental results, such as if you consider flow across a circular cylinder, then through this inviscid flow theory, you cannot predict the flow separation. This theory is unable to explain the existence of the wake, which is the separated region behind the cylinder. Through this theory, you obtain a symmetric pressure distribution, and through this you obtain a zero drag force for flow across a circular cylinder. Whereas in actual condition, there is certain drag force which acts on the cylinder. But through this theory, the pressure distribution which was obtained resulted into zero drag force and zero lift force. And as the approximation is such that you consider negligible coefficient of viscosity, so there is no viscous force in this case, and it follows a boundary condition where the normal velocity is equals to zero, but this inviscid flow theory does not obey the tangential velocity is equals to zero boundary conditions. When we have a no slip boundary condition, we have both tangential for a stationary solid, we have both tangential as well as normal velocity equals to zero. Whereas in inviscid flow theory, we consider only the normal velocity equals to zero. So this theory does not obey the boundary condition corresponding to tangential velocity is equals to zero, which is no slip at the solid surface. Before boundary layer theory, if you look into the analytical solution, were proposed for steady fluid flows. The fluid flows which were not varying with respect to time for steady state situations. And for viscous flow, the analytical solutions were proposed for parallel and row-Reynolds number flow, where the nonlinear advection term, the advection term corresponding to momentum flow rate, are zero, and there is a balance between the pressure and viscous flows, such as in the previous topic on flow in a pipe. When we considered a fully developed flow situation, on uh, the streamwise momentum flow rate, the rate of change, the streamwise change of the streamwise momentum flow rate, the additive term became zero. And for fully developed flow condition, basically had the balance between the pressure and viscous flows. So for such simplest flow situation, we had analytical solutions for viscous flow. And the second class for which we had analytical solution was inviscid flow, as I had mentioned earlier, where you have a balance of inertia and pressure force by solving a linear Laplace equation. This inviscid flow, as I mentioned earlier, predicted pressure distribution on streamlined body that agreed well with the experimental data for flow of fluids with small velocity. However, for fluids with larger viscosity, the pressure distribution uh, did not lead to the non-zero forces acting on the body. This implicit flow predicts zero drag force and non-zero tangential velocity at the surface, and this results do not agree with the experimental results. So note that in boundary layer theory, I'll later on present some analytical methods for obtaining the solution. So before boundary layer theory, there were two analytical procedures, one for viscous flow and another for inviscid flow. And after the advent of the boundary layer theory, so this was the third analytical method of solution for steady fluid flows. If you look into the historical development in fluid mechanics, the Navier-Stokes equation was proposed somewhere in the mid 1800s, and the boundary layer theory was proposed by Prandtl in 1904. Before boundary layer theory, so there were two types of fluid dynamics studies, and these studies were done by two different types of people. The first group of people were mathematicians, and the second group of people were experimentalists. So mathematician, before 1904, when the boundary layer theory was proposed, the theoreticians, the mathematicians, used to consider the fluid as an ideal fluid, where they used to consider incompressible fluid as incompressible and the fluid with negligible viscosity. So they used to consider the viscous force as negligible, and they used to use inviscid flow theory, and the subject, the studies that were done by the mathematician, it was called as hydrodynamics. So in which mathematicians were working on inviscid flow theory. And the group of people who were working on experiment, they called their subject of fluid mechanics as hydraulics. So there were two group of different types of people who were working with different techniques, one theoretician, another experimentalist, and the results which they were obtaining were contradictory in nature. The results obtained by the mathematician near to the wall was not matching with the experimental results. So, but when this boundary layer theory came up, it acts as a bridge between the mathematician and experimentalist, where the results that you obtain from boundary layer inside the boundary layer matches with the experimental results, and outside the boundary layer, the results that was proposed by boundary layer theory matches with the results proposed by the mathematicians. So the boundary layer theory acts as a bridge between the fluid mechanics related with hydrodynamics and hydraulics. Prandtl proposed boundary layer theory with a hypothesis. He said, under rather broad condition, the diffusion or the viscosity effects are significant and comparable in magnitude with inertia force in layers adjoining solid boundaries. So near to the solid boundary, he said that the viscosity effects are comparable in magnitude with inertia forces. The thickness of which approaches zero, that is the thickness of the boundary layer approaches zero, as the Reynolds number of the flow approaches infinity. So as the Reynolds number goes on increasing, the inertia force goes on increasing as compared to the viscous force, and the thickness of the boundary layer reduces. And this viscosity effects are small outside the boundary layer, because outside the boundary layer the velocity gradients are negligible. So even if you have a fluid with finite viscosity, due to the negligible velocity gradient, you have a negligible viscous forces. So his hypothesis said that the viscosity effects are restricted to a narrow region within a solid surface. And this hypothesis is not only applicable near the solid wall, but it is also applicable in, if you consider jets, wakes, and free shear layer. This boundary layer is called as wall bounded layer. So, so the hypothesis which was proposed is in general for a fluid region which has a non-zero velocity gradient. If the region of the fluid with a non-zero velocity gradient is near to the solid surface, then it is called as boundary layer. If the fluid layer with non-zero velocity gradient is away from the solid surface, it is called as free shear layers. So any layer of the fluid which has a normal gradient of tangential velocity, that layer may be near to the solid surface or it may be away from the solid surface. If it is near to the solid surface, we call it as a boundary layer. It's a wall bounded layer. And if it is away from a solid surface, then we call it as a free shear layer. So any fluid layer with a velocity gradient, non-zero velocity gradient, is a shear layer. So now I'll discuss the assumptions for the boundary layer theory and also discuss the importance of boundary layer. The analytical procedure that is used to obtain the solution for using the boundary layer theory. One of the biggest assumption is we consider the Reynolds number as large. Once we consider the Reynolds number as large, the thickness of the boundary layer becomes small, and viscosity effects are confined to a small distance in a transverse direction. And this theory is applicable for no slip condition at the wall, where we consider the tangential velocity of the fluid at the wall is equal to the tangential velocity of the wall. If the wall is stationary, the tangential velocity is 0. If the wall is moving with a constant velocity, then the fluid particle at wall should have a velocity, the same velocity. As I mentioned earlier, for flow or a flat plate, the boundary layer theory, once we calculate the velocity gradient at the surface of the wall, we get the shear force. So that was for a flat plate, but if you consider flow across a cylinder, from the velocity gradient and pressure distribution at the surface of the wall, you can calculate the drag force and lift force acting on for flow across a cylinder or flow across a car or flow across an aeroplane. The understanding of boundary layer can help you to control the flow separation, because this flow separation, later on I'll discuss towards the end of this lecture how we can control the flow separation by the modification of the boundary. Along with the the boundary layer that I presented were where I showed the layer where you have a velocity gradient. For heat transfer problem, you also have a thermal boundary layer, and that thermal boundary layer makes you predict heat transfer between a body and a fluid around it. Now I'll present a scaling analysis where I will show you a derivation of the governing equation for boundary layer, which is called as Prandtl boundary layer equation. And using the scaling analysis, I'll present a the functional form of expression for non-dimensional boundary layer thickness and screen friction coefficient as a function of Reynolds number. Let us consider a free stream flow over a flat plate. So this was the Prandtl model of boundary layer flow. So this is a flat plate, and at the inlet you have uniform velocity. And at a certain location x, let us say this is the velocity gradient, which is gradually increasing from 0 to u infinity. And this is the boundary layer. So at the edge of the boundary layer, note that the velocity gradient, the normal gradient of tangential velocity, is approaching towards 0. So you have a non-zero shear or non-zero del u by del y in this region, but as you move up, this shear is vanishing. Del u by del y is approaching towards 0. The region below this boundary layer is called as boundary layer region, and above is called as free stream flow region, where the velocity gradients are negligible. Boundary layer generates two different length scale. In this problem, note that the length of the plate is one of the length which is known to us. But when you consider a boundary layer, the thickness of the boundary layer is second length scale which is generated. And as in the previous slide I have mentioned, that one of the assumptions which is being used is the thickness of the boundary layer is very small. So this delta is much smaller than the length of the plate. So the boundary layer theory generates two different length scale, delta, boundary layer thickness, and the length of the plate, which have widely varying magnitudes. Delta, this thickness of the boundary layer, is much smaller as compared to the length of the plate. And this is the key to the solution that I'll be presenting using scaling analysis. In the previous topic on differential analysis, I had presented the derivation of this governing differential equation. I had presented the governing equation for 2D Cartesian coordinate system. And the derivation was earlier presented for unsteady flow, but if you consider a steady flow, the time derivative becomes 0. And this is the steady form of the governing differential equation, where for incompressible flow, this is the continuity equation, and this is the x momentum equation, this is the y momentum equation. Where this is like for momentum equation, it's like a fill in the box type of problem, where the term outside the box is same. As you can see, u del u by del x plus v del by del y is same in both this x and y momentum. And here again, you have mu del square u and mu del square v. In the bigger box, you have minus 1 by rho del p by del x. Here you have minus 1 by rho del p by del y. Because it's a transport process where this is the advection term, this is the diffusion term. This gives you the inertia force, this gives you the viscous force, and this gives you the pressure force. The boundary condition is at the solid surface of the plate, if the plate is stationary, u and v are 0. At the inlet, you have a free stream velocity, u is equal to u infinity, v is equal to 0. You have another boundary condition for boundary layer flow, which I'll present in the later slides. Before starting the scaling analysis, let me present the rules of scaling analysis. So let us suppose you have an equation which could be like this. It's basically summation or subtraction. C is equals to a plus b, or C is equals to a minus b, or C is equals to minus a plus b. So if you have an equation like this, and if you consider the right hand side, in the order of, like this O symbol, if I'm using, what I mean is the order of, so this means the order of magnitude of A. So this is the order of magnitude of A is greater than order of magnitude of B. What I mean by order of magnitude is, let us suppose the value of A is 115, and let us suppose the magnitude of B is, let us say, 10, then the order of magnitude of A is 10 to is 10 square, and the order of B is of the order of 10. So if the order of A is larger than the order of B, if let us suppose this is 115 and this is 10, then if you 115 plus 10 will make 125. So the order of C, which is let us suppose 125, is almost same is of the order of A. Okay, so the order of the right hand side, if you have a linear combinations, its order of C will be equal to the or there are three possibilities. The order of C is equal to the order of A is equal to the order of B. If order of A is larger than B, then the order of C is equal to is of the order of A. Okay, so if the order of A is larger, then C will be of the order of A. If the order of A and order of B are same, then the order of C will be same as the order of A and order of B. So let's suppose if this is 150 and this is 120, then if you sum it up, this will also be of the order of hundreds. If you have a, so this was for summation or subtraction. If you have a multiplication, let us suppose P is equals to A into B. So the order of P is equal to the product of order of A and order of B. Okay, so if let us suppose this is of the order of hundreds, this is of the order of tens. If you take the product, then 100 into 10, it will be thousands of order. This will be 10 to power 3 order. So the order of when you have a product, the order of the product is equals to the order of, in this case, A into order of B. Whereas if you take a division, R is equals to A by B, then the order of R is the order of A divided by the order of B. So in a scaling analysis, we will consider, let us suppose, inertia force as C, pressure gradient term as A, and viscous forces as B, and we will use such type of scaling rules to neglect certain terms and come up with a simplified or approximate Navier-Stokes equation, which will be used for, which is here called as Prandtl boundary layer equation. So to derive the Prandtl boundary layer analysis using scaling analysis, these are the variables that we consider: the independent variable, the spatial coordinate x and y, and the dependent variable u velocity and v velocity. You know that the x coordinate is for a flow or a flat plate is varying from 0 to L. L is the length of the plate. Along the y direction, if you consider boundary layer flow, the dimension is varying from 0 to delta. Although this delta is increasing along the flow direction, so this delta is a function of x. So in this case, x is of the order of L, y is of the order of delta. U varies from the maximum velocity you have is u infinity, and inside the boundary layer, the velocity is varying from 0 to u infinity. So u is of the order of u infinity. So this way, before we start, at the start of the scaling analysis, we first obtain the order of magnitude of the various variable: x of the order of length of plate, y the order of boundary layer thickness, u as the order of u infinity. The order of v is obtained from continuity equation. So in a continuity equation, let us suppose for an incompressible flow, two-dimensional incompressible flow, you have two terms. Let us suppose this is A and this is B. So it is like A plus B is equals to 0. This is possible if the order of A is of the order of B. So the order of A here is u infinity divided by L, and here it is V divided by delta. So both this term should be of the same order for to obey this equation. Then only you will get 0. So u infinity by, so this is del u by del x has the order u infinity by L, del v by del y has the order v by delta. So from this scaling rule, you can obtain v as the order of u infinity delta by L, which is shown here. Now using this order of magnitude, we'll apply to the x and y momentum equations. So let us consider the steady state x momentum equation in Cartesian two-dimensional Cartesian coordinate system. So the order of u del u by del x is, or the order of u is u infinity. The order of del u by del x is q infinity by L. The order of right now I'm writing the v as, this is written as v. Although if you this is del u by del y's order is u infinity by delta. If you substitute v is equals to u infinity delta by L, you get u infinity square by L, which is same as the order of the first term. So the inertial term is of the order of u infinity square by L. And here you have 1 by rho, del p by del x is p by, the del p by del x order is p divided by L. This is mu del square u by del x square. Del square u by del x square order is u infinity by L square. Mu del square u by del y square, the order is mu u infinity by delta square. Now, if you see all this term and you apply the condition, as I said, that the key to the derivation is in the boundary layer theory is that you have two length scale of varying magnitude. So delta is much smaller than L. That condition, if you apply to this order of magnitudes that you have obtained for the various term, you realize that if among all this term, when L is much larger than delta, so in the denominator here, if you have L square, so if L is much larger than delta, then if you compare all these terms, so it is like A plus B is equals to C plus D plus E. Okay, so you have 5 different terms, 2 terms on the left hand side, 3 terms on the right hand side. And by doing scaling analysis, what you are finding is that order of A, B, C and E they are of same order. And this term D, since it has L square, and as compared to delta, L is much larger. And here you have L square. In the denominator, you have a much larger value. So if you have something in larger value and that to a square, then the order of magnitude of this term is negligible as compared to the order of magnitude of other terms. So by order of magnitude analysis, we represent this equation, which is like A plus B is equals to C plus D plus E is equals to A as, we simplify it as A plus B is approximately equal to C plus E. So this is the simplified x momentum equation where out of the two double derivatives, we simplified as one derivative. So on the right hand side, instead of 3 terms, now you have 2 terms. Similarly, you can simplify the y momentum equation as this, where your new del square v by del x square is equals to 0. Now, since delta is much smaller than L, so this region inside the boundary layer, delta by L, is a slender region, and the pressure variation intuitively, the pressure variation in the y direction as compared to x direction is negligible. This is derived below. So in general, pressure is a function of x and y. So you can write dP is equals to del p by del x dx plus del p by del y dy. So if you write dP by dx is equals, it is given by this expression. Now, the order of magnitude of pressure gradient in the x and y direction can be deduced from the x and y momentum equation, the simplified form that I had presented, by a balance between the pressure. So when you, so this left hand side is an inertia term. You have, this is a pressure term, and this is a viscous term. So you have 3 terms: inertia, pressure, and viscous term. Out of these 3 terms, so this is like a term, this, let me say the left hand side is A, inertia force is A, the pressure force is B, the viscous force is C. So for this equation is such that the order of A V and C are same. So if you want to know the order of magnitude of pressure, you equate this order of magnitude of this term either with inertia term or the viscous term. Right now, I am showing you a balance between the pressure force with friction, that is the viscous term, but if you balance it with inertia, you get the same result. So if I take the x momentum equation, and in the x momentum equation, I have 1 by rho del p by del x is of the order of mu. Mu is mu by rho. So for the x momentum equation, I get del p by del x is the order of mu del square u by del y square. So del square u by del y square is of the order of u infinity by delta square. Here you y square, so it will be a delta square. And here del p by del y uh, is of the order of mu del square. Note that here you have 1 by rho. This mu is kinematic viscosity, mu by rho. So rho cancels down. So that way del p by del y is of the order of mu del square v by del y square. Del square v by del y square is of the order of v divided by delta square. And from continuity equation, this v is of the order of delta u infinity by L. So if you substitute v is equals to delta u infinity by L, delta square becomes delta, and you get mu u infinity by delta L. So from this, you have obtained the order of magnitude of del p by del x and del p by del y. So if you divide this del p by del y divided by del p by del x, then this mu u infinity in the numerator in both the terms cancels down, and del p by del y divided by del p by del x gives you delta by L, because this in the numerator you get delta L divided by delta square, and finally you will obtain delta by L. So the ratio of the two pressure gradient in the y direction, pressure gradient in x direction is delta by L. But if you multiply this ratio with dy by dx, because here you have a dy by dx, the order of dy by dx is delta by L. So this ratio was delta by L, you got another delta by L, so this is of the order of delta by L square. Now delta by L is a much smaller, is a very small term. So if you take a square of a small term, it will be further smaller. So this indicates that this term is much smaller than this term. So del p by del x dy by dx is much smaller than del p by del x. So if you apply this condition to this equation, what you find that on the left hand side you have a total derivative dp by dx is equals to summation of two terms, del p by del x, which is much larger than the second term from this equation. So if this is much larger than the second term, then this is of the order of, this is almost equal to this term. So you apply this condition and you find that the second term is negligible as compared to the first term. So pressure is varying. So from this you got the del p by del x equals to dp by dx, and so pressure is not varying in the y direction. So del p by del y becomes 0 with these conditions, and pressure is varying only in the x direction. So you can take a point outside the thickness of the boundary layer where pressure is at a particular action location. There is a pressure P infinity. So by taking the pressure from outside the boundary layer, which is P infinity, this dP by dx is converted into dP infinity by dx. So with this analysis, you get a simplified form of the y moment equation, which states that del p by del y is equals to 0. So pressure is varying only in the x direction. So the final simplified equation that we obtained, Prandtl boundary layer equation, in the x momentum equation, here I have written dp infinity by dx, and in the previous slide we have obtained that for y momentum equation, pressure variation in the y direction, pressure varies only in the x direction, there is no variation in the y direction. So this is the simplified x momentum equation, this is the simplified y momentum equation, and in the boundary condition, This is the boundary condition at the ball. This is the boundary condition at the inlet. So if you consider flow over a flat plate, the solid surface, which is the flat plate, is stationary. The velocity u and v are 0. At the inlet, you have u is equals to infinity, v is equals to 0. At the edge of the boundary layer, which we call as far stream, at the edge of the boundary layer, you have u equals to infinity. Now here, the fact that these two boundary conditions, the far stream boundary condition, which is at the edge of the boundary layer, at the inlet, you have u equals to infinity. So these two boundary conditions are same, and due to this simple, and another reason is that if you look into this equation, the highest derivative in the y direction is 2, but the highest derivative in the x direction is 1. So as compared to the x momentum equation originally that we had another term del square u by del x square. So as compared to the original x momentum equation, this simplified x momentum equation has only first derivative in the x direction. So this changes the nature of this equation, and this, as I mentioned, the simplification changes the nature of the equation and makes it amenable to be solved in different ways. So like you for a flow or a flat plate, when you have a free stream and far stream boundary condition is same, then you can propose a similarity variable, and using a similarity technique, you can obtain analytical solution for flow over a flat plate. The similarity solution technique based, I'll not be demonstrating this complete solution, which is outside the scope of this course. But just want to mention that when you have the free stream and far stream boundary condition as same, u is equals to infinity, v is equals to 0, then you can define a similarity variable, and with this simplified form of the equation, you can obtain a semi-analytical solution using similarity technique. You can obtain an expression for the boundary layer thickness and the non-dimensional wall shear stress. I'll not be showing the derivation, but I will later on show you the final expression that is obtained from the similarity solution for flow over a flat plate. So here I had shown you the Prandtl boundary layer equation, which is basically a simplified form of the Navier-Stokes equation, where by using scaling analysis, certain terms are negligible as compared to other terms. Now here I will show you by scaling analysis, we will derive the form of the functional form of the boundary layer thickness and engineering parameters such as wall shear stress. For flow over a flat plate, the pressure everywhere is ambient, so dP infinity by dx. If you consider curved surface instead of flat surface, then you have a variation of this pressure outside the boundary layer along the x direction. So P infinity varies with x for curved surface. But for a flat surface, the variation, there is no variation, and this pressure gradient is equals to 0. So when the pressure gradient is equals to 0, there is a balance between the inertia force and the friction force. And if you do a scaling analysis, the order of magnitude of u del u by del x is u infinity. This order is u infinity by L. So this becomes u infinity square by L. This is v u infinity by delta. Now, if you substitute from continuity equation I mentioned earlier, this v is of the order of delta u infinity by L. So this finally becomes order of u infinity square by L, which is same as this. The friction term, you have nu del square u by del y square, and del square u by del y square is of the order of u infinity by delta square. So if you equate u infinity square by L of the order of nu u infinity by delta square, this is shown here, you end up that delta is of the order of under root of nu L by u infinity, which can be expressed in a non-dimensional form as, if you divide by L, both the left hand side and right hand side, delta by L, here you get u infinity L by nu, which is 1 by square root of Reynolds number. So with this, you have obtained a functional form that non-dimensional boundary layer thickness is inversely proportional to the square root of Reynolds number. This is a very important uh, derivation in a sense that, let us suppose if you are doing an experiment where uh, this you for different Reynolds number, let us suppose you are calculating the boundary layer thicknesses, and um, you finally you want to you can, from the experiment you can obtain the proportionality constant. This is right now a functional form. The actual equation will be delta by L is equals to some constant of proportionality, let us say K divided by square root of REL. So if you are doing an experiment, you can determine that the proportionality constant. So this analytical derivation gives you a functional form of the relationship between the two variables. The independent variable, which is a Reynolds number based on the length of the plate, and the dependent variable, which is a non-dimensional boundary layer thickness. So this gives you an relationship that the non-dimensional boundary layer thickness is inversely proportional to the square root of Reynolds number for a laminar flow. Non-dimensional wall shear stress I have presented in the previous topic on flow in a pipe, where I had presented is a fanning friction factor. But at that time I had indicated that this non-dimensional wall shear stress is also called as skin friction coefficient. The wall shear stress is, as I had introduced earlier, is mu del u by del y at y is equals to 0. So tau w is of the order of mu del u by del y is of the order of u infinity by delta. Now the wall shear stress is non-dimensionalized by half rho u infinity square. Now if you substitute delta from here into this expression, you get tau is of the order of rho u infinity square by REL. Skin friction coefficient is wall shear stress divided by half rho u infinity square. So from this you can get an expression relationship that the skin friction coefficient is inversely proportional to the square root of Reynolds number. So this, by using a simpler scaling analysis, which involves a very simple mathematical procedure, note that you have obtained the functional form of two output parameter in terms of one input parameter, which is a Reynolds number. Okay, so the non-dimensional boundary layer thickness, this is one output parameter, and this skin friction coefficient is an engineering parameter. It's a second output. So both this output parameter through this derivation, they are inversely proportional to square root of Reynolds number based on the length of the flat plate. If you do an experiment or computation, you can obtain the constant of proportionality corresponding to a particular situation. So I started with an introduction, then I had presented the scaling analysis to derive Prandtl's boundary layer equations and expression for non-dimensional boundary layer thickness and skin friction coefficient, where I had shown that they are inversely proportional to the square root of Reynolds number based on the length of the plate. Now I'll present three different types of boundary layer thickness and finally the expression for non-dimensional boundary layer thickness and wall shear stress. So in boundary layer, three different thickness have been proposed. First, which is called as disturbance thickness. So this corresponds to the a different axial location, x location. The thickness is given by the height at which the ratio of u divided by u infinity is 99%. There are two more other thickness which have been defined, which are called as displacement thickness and a momentum thickness. In this slide, I will present a physical explanation of this displacement thickness and momentum thickness. So let us suppose this is a flat plate over which some fluid is entering with a constant velocity. At the inlet, you have a free stream flow. U is equals to U infinity everywhere. V is equals to 0. So as the fluid enters at certain axial location, note that this is at axial location X. This is the velocity profile that you have obtained. Now you can see this is a typical laminar boundary layer velocity profile where finally it is approaching towards U infinity. Now if you, so for the same height, note that I have drawn this velocity profile for the same height of the fluid layer at the inlet as well as at an axial location X. If you compare the mass flow rate, so if you take the integral of the velocity, so if you integral of u dy for an incompressible flow, if you take, so the inlet velocity, so inlet mass flow rate is larger for the same height of the fluid layer. So this is the thickness of the boundary layer at an axial location x, delta x. This is the m in is the mass flow rate at the inlet. Mx is the mass flow rate at axial location x. Now, if I draw a streamline which is starting from the inlet at the same height at which I am showing you this velocity profile. So this is height, let me denote as delta. So if you consider a streamline which is starting from the inlet, now the bottom wall of the flat plate is also a streamline, and the streamline is a line along which the flow, it gives you the direction of the flow, and the volumetric flow rate between two streamline is same. So the streamline, you have one streamline which is above and passing through the top surface of the plate, and this is another streamline which is passing from the height h is equals to delta at the inlet. Now if you now the streamline, if you see, it is basically increasing its height as it is moving over the plate. So at this location delta x, the displacement, the vertical displacement of the streamline, because as I said that the difference between two stream, the value for a particular streamline, there is a particular value of stream function. We have one stream function at the top surface of the plate. You have one streamline at the top surface of the plate, which has some stream function value. This is another streamline which has some other stream function value. Now the difference of this, so if you take the integral of u dy at this location, and so this is the vertical displacement which is above the boundary layer, which is called as the displacement thickness. And if you take the integral of the velocity, now outside the boundary layer, the velocity is u infinity. So outside the boundary layer, if you want to calculate the mass flow rate, it will be u infinity into delta star. So this displacement thickness corresponds to a vertical displacement outside the boundary layer, where such that corresponding to this vertical displacement, the mass flow rate is equal to the difference of inlet mass flow rate and the mass flow rate at this axial location. If you consider x, the streamwise momentum flow rate, the streamwise momentum flow rate is given by the mass flow rate multiplied by the velocity in the horizontal direction. So mass flow rate multiplied by velocity is equals to, this is like an x momentum flow rate. Now at this location, the x momentum flow rate will be given, mass flow rate is given by integral of u dy. Momentum flow rate is given by integral of rho u square dy. So if you, as I mentioned earlier, for the same height, the mass flow rate is less as compared to inlet. Similarly, the x momentum flow rate is also less than the x momentum flow rate at the inlet. So if you consider a x momentum flow rate based line, so let us suppose you have a momentum function where uh, the delta double star, the momentum thickness is the increase in the height, the displacement of this momentum function line over and above the displacement thickness, such that if you take this complete height and take the integral rho u square dy instead of, so if you take integral of 0 to delta plus delta star plus delta double star, then the x momentum flow rate at this axial location x and at the inlet there will be a quite perfect balance. Okay, so this displacement thickness and momentum thickness are basically related with the thickness outside the, or the vertical displacement, or basically the height of the fluid layer outside the boundary layer, which is needed to compensate for the decrease in the mass flow rate for displacement thickness and decrease in the momentum, the streamwise momentum flow rate uh, outside to so, so this distances, additional distances basically compensate for the decrease in the mass flow rate and momentum flow rate that occurs at a certain axial location x. So the displacement and momentum thickness are the vertical displacement of the streamline and streamwise momentum function based lines, so that there is a balance between the mass flow rate at the inlet and at an axial location x. The displacement thickness is a vertical distance by which the streamline with a height h is equals to delta at the inlet are displaced due to the presence of the boundary layer. And as I mentioned, this is if you take the difference of the stream function, let's suppose psi1 is the value of stream function at the top surface of the plate, and psi2 is the stream function uh, corresponding to the height h is equals to delta at the inlet. Then the difference of the stream function is basically equal to the volumetric flow rate. So this is the volumetric flow rate at the inlet, uh, and so it will be basically equal to U infinity into delta. Then this is equal to integral of u dy. This is at axial location x, 0 to delta plus delta star. The additional height delta star is basically compensating for the decrease in the mass flow rate for the same height corresponding to the inlet. From this you can derive delta star, that is displacement thickness, is equals to integral of 0 to delta 1 minus u by u infinity dy. This momentum thickness is a vertical distance by which the contour of streamwise function momentum with a height h at the inlet are displaced in addition to the displacement thickness. Note that this delta star, the integral that you have to do is equals to 0 to delta plus delta star plus delta double star. So this is in addition to the displacement thickness due to the presence of boundary layer. So this is the integral which will give you the x momentum flow rate at the inlet, and this is the integral which will give you the x momentum flow rate at an axial location x. So basically this delta star and delta double star are the additional height outside the boundary layer which are needed to compensate for the decrease in the mass flow rate and the decrease in the x momentum flow rate. And through this you can derive the momentum thickness as integral of 0 to delta u by u infinity 1 minus u by u infinity dy. So in the previous slides I had shown you the definition of the three different thicknesses. Displacement thickness is represented by delta. It corresponds to a height of the fluid layer at which the ratio u by u infinity is 0.99. The displacement thickness and the momentum thickness, I had shown you the derivation in the previous slide. And these are the expressions which have been derived in the, previous slides. Finally, I had mentioned that using a similarity technique, you can derive the relationship, the mathematical relationship for the boundary layer thicknesses and the local skin friction coefficient. Uh, in the final expression that has been obtained for laminar flow and for turbulent flow. For a turbulent flow, as I mentioned, it's a much steeper velocity profile. So if you use a 1/7 power law turbulent velocity profile, then from using similarity techniques, these are the expression for non-dimensional disturbance thickness. Delta by x is equals to 5 divided by under root Rex for laminar flow. And this delta by x is almost equal to 0.16 divided by Rex to the power 1/7. These are the displacement thickness. This delta is disturbance thickness, delta star is displacement thickness, delta double star is the momentum thickness. So these are the expressions for non-dimensional displacement thickness for laminar and turbulent, and these are for momentum thicknesses. The local skin friction coefficient, which is the non-dimensional local wall shear stress, which varies along the length of the plate. It is, as I mentioned in previous slide, that it is inversely proportional to the square root of an odd number. And from similarity analysis, the constant of proportionality has been obtained as 0.664 for laminar flow, and for turbulent flow, the skin friction coefficient, instead of square root, it is 7th root, and the constant of proportionality is 0.027. So here I'm showing you the final expressions for the non-dimensional boundary layer thickness and non-dimensional wall shear stress for laminar and turbulent flow, which have been obtained using a similarity technique. So after finally, I'll present the important fluid dynamic phenomena, which is called the separation of boundary layer. First, I'll draw an analogy before presenting the separation of boundary layer. Let us suppose you consider a metallic ball which is rolling over a U-shaped container. So let's suppose this is a ball, and you can have two situations. If this container surface is extremely smooth, then you find this type of situation where basically the ball drops and then it lifts up. So in this case, the potential energy gets converted into kinetic energy when it comes down. And then the increase in the kinetic energy gets converted into potential energy. So there is a complete conversion of the potential energy to the kinetic energy and again back to the potential energy. If the surface of this container is extremely smooth, it is frictionless. However, if it has friction, then what you find that the kinetic energy does not get completely converted into potential energy. So similar to this situation where you have interchange between the potential energy and kinetic energy, when you consider flow across curved surfaces such as this is a flow across an object which is of circular shape, which is called a circular cylinder. So in this case, if you consider a streamline, let us consider a streamline near to the solid surface, and as I had mentioned earlier for flow over a flat plate, that the surface of the solid surface of the top surface of the flat plate for the previous problem, and in this problem the circumference of circle, you have a streamline, and this is another streamline, and between two streamline the fluid cannot flow across the surface of the streamline. So when the fluid cannot flow across the surface of the streamline, whatever fluid is entering, you can see that so this is like a internal flow situations where between the two streamline, and we know that the fluid cannot penetrate a streamline, so it has to pass through this cross-sectional area. Now you can see that when the fluid is, so in this case the problem is you have a free stream flow across a circular cylinder. Similar to the previous problem for flow over a flat plate, let us suppose there is an inlet, U is equals to U infinity, and this cylinder is stationary. So when the fluid passes over the surface, so in this case, between the two streamline, the fluid, in this case, you can see that the cross-sectional area is reducing. And if you, let us suppose, apply the Bernoulli's equation, if the cross-sectional area is reducing, and in a Bernoulli's equation, you have a pressure head, kinetic head, and you have a potential head. Let us say the change in the potential energy is negligible as compared to other head. So then you are left with kinetic energy and pressure energy. Here you have potential energy and kinetic energy. So in this case, when the cross-sectional area is reducing, and if you have an incompressible flow, then if you can use a formula A1V1 is equals to A2V2 for an incompressible flow. So when the cross-sectional area is reducing, the velocity has to increase by volume conservation. So when the fluid moves in between the two streamline from here to here, its velocity is increasing, so its kinetic energy is increasing. So if you consider the Bernoulli's equation with negligible change in the potential head, then the increase in kinetic energy will lead to decrease in the pressure energy. So here, from when the fluid moves from here to here, its velocity is increasing, pressure is reducing, and in this, on this side, you see that now the cross section is increasing. If you see the gap between the two streamline, it is increasing. So in this, it's a diverging flow. Here it's a converging flow. Here it is like a nozzle, and on this side, it's more like a diffuser. So when the fluid is accelerating here, and it's a decelerating here. When the fluid is accelerating, the pressure is reducing along the flow direction. Velocity increases, pressure decreases. On this side, velocity decreases, pressure increases. So pressure is increasing along the flow direction. Okay. So here X is considered as tangential and Y is considered as normal to the surface. So if you take 3 points A, B, C, where this X1 is the tangential direction, Y is the normal direction. And so you have 3 different regions. Here, so let us put this here, theta is equals to 0. This is theta is equals to 90. And this is from here to here, theta is varying from 90 to 180 degree. So between theta is equals to 0 to 90, which is between, this is 0, this is theta 90. So from here to here, you find that you have a converging flow, which means the velocity is increasing, the streamwise velocity is increasing, the pressure is reducing. So the pressure is reducing along the tangential direction. So del P by del X is negative. So it is like you are moving on a road where on the front side, let's suppose you are on your front side, pressure is less, and on the back side, pressure is more. So this is an example. So if you consider yourself as a fluid particle, you are moving upward, and what you are finding is the pressure ahead of you. Let's suppose if this is a fluid particle, it is moving. The pressure ahead is less. The pressure behind is more. So you have a net pressure force which will push you along the flow direction that leads to the increase in the velocity. So this is called as a favorable pressure gradient because it leads to an acceleration of the fluid particle. Now, if you look into theta is equals to 90 degree, at near to the 90, you find that the cross-sectional in which the fluid is moving is almost same. So here you have a almost zero acceleration, and you have a pressure gradient is equals to 0. And from here to here, you have a diverging flow from 90 to 180. You can see that the gap between the two streamline, it is increasing. And when the gap is increasing, it means for an incompressible flow, the velocity has to decrease and the pressure has to increase. So between 90 to 180 dP by dx, the pressure is increasing along the flow direction. So dp by dx is positive. So when dp by dx is positive, when the fluid particle is moving in the forward direction, it is finding that on the front space, it has a larger pressure. So there is a net pressure force which is resisting the direction of motion. So, so between in this region, when you have a favorable pressure gradient, if you compare the various forces, as I mentioned in the previous equations when I introduced, there is an inertia force which is on the left hand side, there is a pressure force on the right hand side, and viscous force on the right hand side. Inertia force always acts along the flow direction. The viscous force always acts opposite to the flow direction because it's a resistive force. It comes due to the stickiness between the different layers of the fluid. Now, between 0 to 90, you have a del P by del X less than 0, which means along the flow direction, pressure is reducing. So there is a net pressure force which is pushing the fluid, which leads to the acceleration of the flow. So the pressure force, when you have a del P by del X negative, it is like, let us suppose this is a fluid particle. If this is negative, it means on this side you have a low pressure, on this side you have a larger pressure. So there is a net pressure force which acts on the flow direction. So this is the direction of the pressure force. Inertia force always acts in the forward direction. Viscous force acts in the opposite direction. So between 0 to 90 degrees, when you have an adverse pressure gradient, this is the direction of the forces. When the pressure gradient is 0, the net pressure force is 0, and there is a balance between the inertial force and viscous force. Now, when you go to 90 to 180 degree, when you have an adverse pressure gradient, as I mentioned, that the inertial force always acts in the positive direction, viscous force always acts in the negative direction. However, when you go from favorable to adverse pressure gradient, note that the direction of pressure force reverses. So here in this case, favorable pressure gradient is in the forward direction. When it becomes adverse pressure gradient, the direction of pressure force in the negative x direction. So under this situation, the pressure force is resisting the inertia, and depending on the strength of inertia and the strength of resistance offered by the adverse pressure gradient, the fluid which is near to the wall, its velocity reduces, and initially it is on the forward direction near to the wall, but due to the adverse pressure gradient, the near to the wall, the velocity reduces, and when the flow separation takes place, the velocity near to the wall of the fluid, uh, the flow near to the wall reverses its direction. There is a flow reversal, which I will show you in the next slide. So this between 90 to 180 degree, when you have a dp by dx greater than 0, where you have a diverging streamline, you find that you have an adverse pressure gradient. And here it's likely for the flow to get separated depending on how much adverse the pressure gradient is, and also upon what is the inertia of the flow near to the wall. So note that the necessary condition for flow separation is adverse pressure gradient, but the separation is not guaranteed, such as if you are considering flow in a diffuser, which is a pipe of diverging cross-sectional area. Depending on the angle of divergence, if the angle of divergence is large, then you have a much larger dp by dx, and then it's more likely to be for the flow to get separated. It also depends on what is the flow velocity which is passing near to the wall. So dp by dx is a necessary condition. So flow separation can never occur in a nozzle where you have a dp by dx negative. It may occur in a diffuser. However, the sufficient condition for flow separation is at y is equals to 0 at the surface, the normal gradient of tangential velocity del u by del y should be equal to 0, which I will show you in this slide. So influence of pressure gradient on the velocity distribution within the boundary layer. I will show you the velocity profile of velocity, its slope and curvature. So this is a case where you have favorable pressure gradient. Pressure is reducing along the flow direction. So there is a net pressure force which will push the fluid and lead to the acceleration. So in this cases, you get a velocity profile like this, where the slope is monotonically reducing. When I say slope, I mean del u by del y. This is the u velocity in the x direction, and vertical coordinate is y. So you can see this is a velocity profile, u as a function of y, and del u by del y is monotonically decreasing. Here in this case, when you have an adverse pressure gradient, as I mentioned, that near to the wall, the fluid have least inertia as compared to the above layer of the fluid, and they are more susceptible to the effect of pressure gradient. And if you have a adverse pressure gradient, basically the net pressure force will decrease its streamwise momentum, and when near to the wall, in this case you can see del u by del y at wall is equals to 0. So this is the sufficient condition. Under this condition, you can say that there is an onset of flow separation. So note that del u by del y is when you have this condition, then it is guaranteed that the flow separation has occurred. Okay, so del P by adverse pressure gradient is a necessary condition, and the normal gradient of tangential velocity is equals to 0 at the solid surface is the sufficient condition for flow separation. This I had shown you the profile of velocity. Now I'll show you the profile of its slopes. So I'll show you, this is the figure of del u by del y. So as I mentioned, that in this case, del u by del y is positive near to the wall, and it approaches a constant value. Whereas when you have an adverse pressure gradient, initially you can see that the slope of this curve del u by del y is increasing up to certain height, and then it is decreasing. So as shown here. And if you compare the curvature, you can see that there is monotonic way. Its curvature is monotonic. It is always negative. But here in this case, near to the bottom wall, you have a positive curvature, and above you have a negative curvature. So if I plot curvature del square u by del y square for favorable pressure gradient, the curvature is always negative. Near to the wall, curvature is large, and it asymptotes to a zero curvature. Whereas for an adverse pressure gradient, near to the wall, you have a positive curvature, and on the upper side, you have a negative curvature. So there is a change in the magnitude of the curvature from negative to positive, and this is called as point of inflection, the point across which there is change in the sign of the curvature. So the variation of curvature of velocity profile within the boundary layer, at the edge of the boundary layer, as the velocity profile has to blend with the external profile, del square u by del y square is less than 0, that is curvature is negative, always negative. At the surface of the cylinder, you could have two conditions. If you have a favorable pressure gradient, accelerating stream, then near to the wall also you have a negative curvature. Whereas for a adverse pressure gradient, where you have a decelerating stream, the curvature near to the wall is positive. So the curvature of velocity profile changes sign somewhere within the boundary layer as a point of inflection, which I had demonstrated in the previous slide. Now in this slide, I'll discuss the reason for increase in the thickness of boundary layer in the decelerating flow region. Compared to a flat plate, a decelerating external stream. So as I mentioned, that the deceleration can occur when you find that the streamlines near to the solid surface are expanding. So it's like the cross-sectional area between the two streamlines near to the solid surface is increasing. Then there is a decelerating external flow causes a larger del u by del x within the boundary layer. So when you have an adverse pressure gradient, the pressure force tries to reduce the streamwise momentum or the streamwise momentum flow rate. That leads to a larger del U by del X within the boundary layer, because the deceleration of the outer flow add to the viscous deceleration within the boundary layer. So, and from the continuity equation, you have del U by del X plus del V by del Y is equals to 0. And in under adverse flow conditions, when you have del U by del X larger, then to balance it, del V by del Y also has to be larger. So it follows that V velocity is larger for the decelerating flow. So boundary layer thickens not only by viscous diffusion, but also by advection away from the surface. The rapid growth of the boundary layer and the associated large V velocity causes separation, where the external stream ceases to flow parallel to the wall. Near to the wall, you have a reverse flow situation when the flow separation occurs. Finally, I'll present there are certain techniques to control the boundary layer separation, because the boundary layer separation is undesirable because it causes a low pressure region at the surface. And but under certain condition, depending upon an application, we may want the flow separation to occur. So we have certain techniques to control boundary layer separation, either to suppress it or to initiate it. Like one of the technique is called as boundary layer tripping. Like one of the common example is, if you consider a cricket ball, you have a seam, and on one side of seam we make the ball rough, and on the other side we keep it smooth. So when the so when the flow passes along the seam and it goes to the rough side, then the seam acts like tripping of the boundary layer. Tripping is basically um, uh, an action which causes the laminar boundary layer to transit to a turbulent boundary layer. So when the ball is thrown, the flow when it passes to, across the seam, there is a transition of the laminar boundary layer to the turbulent flow, because not only it passes across the seam, but it also moves to the from the smooth region to the rough region. So after passing the seam, the boundary layer is stripped, and there is a disturbance which is created, which causes the laminar boundary layer to transit to the turbulent flow region. And when if you compare the laminar boundary layer versus turbulent boundary layer, the turbulent boundary layer I had mentioned earlier, they have much larger acceleration near to the wall. So the flow separation in turbulent boundary layer as compared to laminar boundary layer is delayed. So when you consider a cricket ball across the seam, when the transition takes place and then the fluid passes through the rough sides, the flow separation on one side is delayed, and that leads to in-swing or outswing. So and the second technique is, if you do a better streamlining, like the circular cylinder on the back side, if it instead of circular, if you could have made it like a triangular, then basically you are decreasing, it's like decreasing the increase in the gap between the streamline. So when you make the surface more streamlined so that the fluid, there is a gradual change in the gap between the streamline. So in those cases, that even if there is an adverse pressure gradient, it will not be sufficient enough for flow separation. Another technique is wall suction, where basically you suck the low momentum fluid near to the wall, and which is displaced by the high momentum fluid above it. So you always find that the fluid near to the wall have sufficiently large streamwise momentum to overcome the adverse pressure gradient. The opposite of wall suction is if you push some fluid at the wall, then you are basically adding streamwise momentum to the near wall fluid, and the increase in the streamwise momentum of the near wall fluid will help it to sustain the adverse pressure gradient and avoid flow separation. So this wall suction, wall blowing, and streamlining are some of the techniques which are used for avoiding flow separation. And this boundary layer tripping is mainly a technique to convert the laminar boundary layer to a turbulent boundary layer, where in a turbulent boundary layer the flow separation is delayed, and in certain cases it could be avoided. With this, I had come to the end of this lecture. Thank you for your attention. For this topic, I have referred this book by Muralidharan Biswas, Advanced Engineering Fluid Mechanics. Thank you for your attention.